So our last topic in probability will take us 2 days to go through. We'll do a basic style problem today and expand it more tomorrow. Generally with probability, we tend to sample without replacement, but often we can do probability problems that involve sampling with replacement or doing events that don't have any effect on each other. So what we're going to do is build this law for what we call binomial probability. And here's how it works. So let's look at exercise 1. Consider tossing a standard coin and then rolling a standard 6-sided die. For part A, we're going to write the sample space using a list of ordered pairs. So let's think about when we flip a coin. First, it might land heads up, and we've also rolled a die. So when the coin lands heads up, the die could have a 1, a 2, a 3, a 4, a 5, or a 6. And the same thing can happen if the coin had landed tails up. The die could still land 1 through 6. Okay, so for part B, we're going to determine the probability of getting a head and a number less than 3. Well, here are all the ways I can get the coin to land heads up, and the number less than 3 is either 1 or 2. So there are 1, 2 instances of a head and a number less than 3 out of 12 total possibilities, which, again, if you want to, you could reduce to 1/6. Doesn't matter. For the next part, what are the individual probabilities of getting a head and getting a number less than 3? Well, in this case, in order for the coin to land heads up, that probability is 1/2. And the probability of getting a number less than 3 when I roll a die is 2 out of 6, or 1/3. For part D, how could I combine my answers in part C, or how could I use those answers to calculate what I got in part B? Well, if I were to multiply the probability of the coin landing heads up times the probability of the die landing on a number less than 3, I would get 2/12 or 1/6. And again, the key word here is it's and. The probability of the coin landing heads up and a die getting a number less than 3. And means multiply. So this author gives us a general form of a formula. I'm not too big on formulas. I like us thinking through things. But the probability of a sequence of events is equal to the probability of the first event times the second event times the third event, all the way to the number of events you have. We're going to use this to build the actual rule of the day. Okay, so let's look at the next problem. On a 5-question multiple choice test, there are 4 choices per question. What is the probability of getting exactly 3 of the 5 questions correct? And it should really say by merely guessing. We're just kind of assuming you don't know anything, you're going to guess. What's the chance that you'll guess 3 out of the 5 questions correct? Well, the probability of guessing correct is 1/4, because there's 4 choices and only one of them is correct, which means the probability of it not guessing correct is 3/4. Probabilities of an event and the opposite of the event always add up to 1. Okay, let's see. So what do we want to happen? We have 5 questions, and we're checking the probability of guessing exactly 3 out of the 5 correct. So I could guess the first one correct, second one correct, third one correct. There's my 3 correct. But in a 5-question test, that means I guessed 2 of them incorrectly. I could rewrite that, clean it up, as 1/4 cubed. I have 3 guesses correct, and times 3/4 squared. 2 of my guesses were incorrect out of the 5-question quiz. Now, I'm choosing from 5 questions 3 that are correct. So I also need to include the combination that shows there are 5C3 ways of choosing those problems that are correct because of these orders. So I would say 5C3 times the probability of getting a question correct, 1/4. And again, we want that to happen 3 times. Notice these numbers are the same. Times the probability of not guessing correctly, 3/4. If I have a 5-question test and I guess correctly 3 times, then I'll be wrong twice. These two numbers, the two exponents, always add up to that bottom number. And then you would do the math. The setup's the hard part, that's the new part. And you end up with 10 times 1/64 times 9/16, which unreduced is 90 out of 1024. Always unreduced is fine, but your calculator will often reduce for you, and this would go to 45 out of 512. So that's the idea behind what we call binomial probability. We have the number of possible things I'm looking for being successful at, combined with how many successes I'll have. The probability of success, which is whatever I want to happen in the particular case. Here it's guessing correct. Raised to the number of times I need to be successful, times the number of failures. Here not correct, raised to the number of times I'm going to fail. That's the general way to think through it. Let's look at another. So of course there's a formula for this, and there it is, your binomial probability formula. It's exactly what we just did. NCR times, we call P our probability of success, raised to the R, so these numbers are the same, times Q, which we call our probability of failure, raised to the N minus R. These two numbers subtracted so that your exponents will add up to the possible cases. Notice that probability of success and failure always add up to 1. Okay, so let's just try some. On an equatorial island, it rains very consistently. If the probability of rain on any given day of the week is 2/3, find the following. So the first thing I do is I think about those probabilities. We're talking about probability of rain, which in this case is our probability of success. And they give that to me as 2/3, which means the probability of failure, or no rain, is 1/3. Again, these numbers always have to add up to 1. Now the question's asking, what's the probability it will rain on exactly 5 out of 7 days? That is your combination setup. Out of 7 days, I'm wondering about 5 rainy ones. So 7C5 times the probability of success, or rain in this case, 2/3, to the 5th. I'm wondering about 5 rainy days. These numbers have to match. Times the probability of failure, 1/3. Well, if I'm successful 5 out of 7 times, I'll fail twice out of 7 times. So again, that is your setup. That's the new part for today. And you do need to show your success-failure ratios. And then from there, it's simple calculator punching. You'll get 672 out of 2187, or reduced to 24 out of 729. So let's find the probability that it will rain on exactly 1 of the 7 days of a given week. So my success and failure are not going to change. It's the same problem. But here it's the combination that changes. Out of the 7 days in that week, I'm only curious about rain on 1 of those days. So now my combination is 7C1. I'm only going to rain once in those 7 days, so my probability of success 2/3 to the 1st, times my probability of failure 1/3 to the 6th. If it rains 1 out of 7 days, it does not rain 6 out of 7 days. Again, you clean that up, and you get 14 out of 2,187. Okay, let's do number 4. Which of the following represents the probability of getting exactly 4 heads when flipping a fair coin 8 times? Well, when I flip a coin, the probability of it landing heads up, here, that's our success, is 1/2. So the probability of tails, or failure, is also 1/2. I'm curious about the probability of it landing heads 4 times out of 8 flips. So that's 8C4 times your probability of success to the 4th, times the probability of your failure also to the 4th, because if you are successful 4 times out of 8, you fail 4 times out of 8. Punch that into your calculator, and you get 35 out of 128. Okay, so I'll do one more with you and have you try the last one on your own and check against mine. Number 5, Michaela has the probability of making any free throw in a basketball of 80%. So her probability of success is 80%. We'll change that to a decimal, 0.8, which means the probability of failure is 0.2. She shoots 6 free throws in a game, which is the closest to the probability that she'll make exactly 4 out of the 6. That's our combination. 6C4 times your probability of success, 0.8 to the 4th, times your probability of failure, 0.2. That will be squared because these exponents add up to the total number of trials. Again, use your calculator. You get 0.24576 as a percentage. Move your decimal, and that's about 25%. Close 4. So at this point, you should pause the video, try number 6 on your own, and then unpause and check your answer against mine.